All right, this is video 3 of a 3-video series about applications of derivatives. This one is about related rates, and it takes the ideas from implicit differentiation and the ideas from the chain rule and kind of mixes them all together so that we're actually starting to do real-world application problems in action. These look really intimidating at first. You will need to practice them and really dig in for them to make sense. The more you practice them, the easier they will get, the more intuitive they will become. I still stumble over some of these problems sometimes, so don't be afraid, but be highly organized. The more organized you are, really the better that it'll come out. And I've got some tips in here for you as you try your own related rates problems. All right, so here's an idea of some type of related rate problems. This is a classic problem. So you just filled a paper cup of water that is shaped like a cone, but it's the last one and it has a hole at the bottom. So it's actually dripping out a ton of water. And the water keeps coming down and the height of this gets smaller and smaller. You can't plug the hole. You need to bring your brother enough water to take his medicine, but by the time that you fill the cup and you bring it up to him, the cone is only about halfway from the top. Will you have enough water to bring him? Will you be able to bring him enough water to take his medicine? So this is a classic problem. We're not going to do this problem, but we're going to do 3 others, and you will see this one in class. I guarantee it. We'll either do it as a class, or you can find this particular problem all over the internet. Related rates are some of the most useful tools in calculus because they relate 2 or more things, often including a third part, which is oftentimes time. So time is often this third part that's not in consideration in most math problems, but with related rates we will use it. Many word problems can be used, worldly problems. So anytime you're managing information or you're doing something for a company and you're trying to figure out when something's going to run out, or when is something going to overflow, or how fast is something happening. These are tricky at first, but a lot of practice, they become a lot easier. So take the time. We're going to go over 3 problems, and we're going to do one, and then I'm going to give you some tips, and then we're going to do 2 more. So I'm just going to read through this problem, and I'm going to annotate as we go. A pebble is dropped into a calm pond, causing the ripples from the center. I'm going to quickly draw a picture of that because I know how water moves, and it starts and my pebble gets dropped and then it goes out and out and out. And so there's a picture of what I'm visualizing as I read this. So the radius of the outermost ripple. Okay, so I'm thinking about radius. The radius of the outermost ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? So we've got something, radius is 4 feet. When the radius is 4 feet, so r is going to equal 4 at some point in time, and the outermost ripple is moving at a constant rate. So I'm told a rate to begin with. The radius of the ripple, the radius of the ripple per time being seconds, is 1. Okay, so I've got a lot of stuff going on here. So I added this grid, and again, we're thinking about 1 foot per second. We know that the change of the radius over time, it's changing at a rate of 1 foot per second. And the radius that we know currently is 4, so I think r equals 4. I'm going to make a quick diagram here. I've got my pond and my radius. We know the radius is 4. And we know something, we're looking for the area, the total area. Something that is not explicitly stated in this problem that I think will be very useful is the formula for the area of a circle. So the area of the circle is pi times the radius squared, so pi r squared, and that's going to be really helpful. So I've got a grid to help a kind of a tool, if you will, to help me make sense of all of the pieces of this problem. Knowing that there's a lot going on, I want to be really, really careful about the things that I know and the things that I have access to. So one of the known descriptors is I know the radius of the pond. So I'm going to say the radius of the pond. I know the radius of a circle is represented by r, and the radius I know to be the value is 4, and the units of the radius for this pond are in feet. Another thing that I know that might not be super duper obvious is I actually know the area of the pond at the moment that I'm interested in. So I know the area of the pond. We called that A, and in this particular problem they used a capital letter A. We don't know what it is, but the area is going to be always is in feet squared, or squared feet, or feet squared, or square feet. Actually, I will write it as square feet, just so that we're not getting confused. Square feet. And how do I know the area of this pond? Well, the area when the radius is 4 is pi times 4 squared, which is 16 pi. So I know the area is 16 pi square feet because I implemented my problem. Okay, what else do I know or want to know? Well, I'm told that the outermost ripple is increasing at a rate of 1 foot per second. So I actually know the change in radius, the speed the radius is changing over time. So I'm going to go the change in the radius over time, which we measured in seconds. And we know that the change in the radius over the change in time, we were told in this is 1, and it's feet per second. Last but not least, the thing that we don't know, the thing that we're looking for is the rate of area. How fast is the rate of area changing? So we're looking for the change in the area over some amount of time, but only at the time when the radius is 4 feet. So how fast is it changing exactly when the radius is 4 feet? And this is our thing of interest, the change in area over the change in time. And this is actually the one thing that we don't know, and the area is going to be changing at a rate of square feet per second. Okay? This gets really interesting really fast. So I have no way currently to relate the derivative of, I don't even know what this is. I don't have any way to relate this to this because I don't even know where I can find this. Here's the key, and I'm going to highlight it in red. This is it right there. That formula, which wasn't even given to you, but you should know, is the key to this entire thing. And all we need to do is take the derivative of A with respect to t. So if I'm going to do, if I'm going to do the derivative with respect to time of A, and I'm going to do the derivative with respect to time of the pi r squared, the derivative with respect to time of pi r squared, notice this is where the chain rule and implicit differentiation come in more than anywhere else, that this is a derivative with respect to time. I don't know how A is related to time, so I need to be really, really careful, and I'm going to use Lagrange notation. So this is dA dA, capital A, dt. And the derivative of pi r squared, well, pi is not a derivative. Pi is a constant, so the pi is going to stick around. The derivative of r squared is 2r. Implicit differentiation, I got to use the chain rule, dr dt, because the change in the r is a function of time, because as the ripples go out, the radius is changing, and time and radius are very related, hence related rates. This is where it kind of all comes together. So we've taken the derivative of my original of the formula for the radius of the square, taken the derivative, I've gotten this. Hey, I now have a way to relate dA dt to all of the other information that I have. And all it is at this point, I know what r is 4. I know what dr dt is 1. I didn't seem to need this information, but I could have potentially needed it at some point in time. So what is dA dt? dA dt is pi times 2 times the r from the table times the dr dt, which is just 1 in this particular case because it came from our table right here. Dr dt is 1. And I get my dA dt, which ends up being, and I'm going to leave the pi in there, and if you want to change the pi to be 3.1415926, blah, 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 so on and so forth, you can, but my answer is just 8 pi. And that is the change in the rate of area at time in feet per second. So the area is changing at 8 pi square feet per second, exactly when the radius is 4. Sounds like a mouthful. So you can see how complicated these problems look. The more you practice them, the better, the easier they will become, the more they will start to make sense. I'm going to give you some tips. You may want to write some of them down. Tip number 1, in fact, is use a table and organize your thinking before you even begin starting. And another tip is to draw a picture. So here are some tips when solving related rates problems. Tip number 1, identify all of the quantities and that are given and the quantities that you need to find out moving forward. Tip number 2 is make sure to sketch the situation. I drew circles in my pond, and so you could see, I could kind of visualize the problem. Some you need that visualization less, sometimes you need that visualization more. Write down any formulas you know that are related to the problem. I didn't know that I needed the area of the circle until I was like, hey, what is the area of a circle for a given radius? Tip number 4, you use the chain rule to differentiate with respect to time almost always. Rates always have a time element, so maybe it's seconds, hours, minutes, whatever it is. Time is almost always a part of a rate, so take advantage when you use the implicit differentiation. Tip number 5 is substitute all of the knowns that you've got into the equation and then solve for the value that you're interested in. So now this is kind of like in the recommendation for steps to solving the problem. So once you've made a sketch and you wrote everything down and you use the chain rule, substitute things you know. Related rates are really tricky at first, and it's super important that you're organized when you're solving them. That's why I made a table. So we're going to go through 2 more problems. And some of these have better pictures that are associated with them. Sometimes the problem giver will give you a picture, and sometimes you're going to be required to write them on your own or draw the pictures on your own. All right. This case is about a balloon, and it's being filled up. Air is being pumped into a spherical balloon at a rate of 4 cubic feet per minute. Find the rate of change of the radius when the radius is 2 feet. So I'm going to just automatically, I know that we're going to be thinking about volume because air is going into a cubic space. So I decided to write down the volume of a sphere is 4/3 pi r cubed. And then I'm going to annotate really quick. I'm going to read it one more time, and I'm going to annotate as I go. Air is being pumped into a spherical balloon at a rate, I'm given a rate, 4.5 cubic feet per minute. Oh my gosh, I've got volume and a rate associated with that volume. This is going to be super helpful. I know that radius has something to do with it because I'm told radius is 2 feet, and I'm looking for the rate of change of the radius. So those are the things that I know and the things that I'm looking for. So I'm going to start filling in my table. I know the radius. I know the radius is with a letter R. The radius that I am sure of right now is 2, and radius is in units of feet. And I'm just copying things into information that I know. I know that I can find the volume, and volume seems to be a big piece of this. Volume is with a V. Volume is cubic feet. And you might be saying, why isn't it cubic feet per minute? Well, volume isn't a rate yet. I do have a rate. The change in volume, over time. I'm told that. And the time is minutes, by the way. And this is I just want you to know that this picture doesn't do it justice. This is actually a very large balloon. If we're going at the radius of a balloon is 2 feet. Imagine a 2-foot balloon. The change in volume over change in time. This is where we kind of have to start making up things that we don't know, or making up ideas. So the change in volume over the change in time, the change in volume over change in time. Hey, I've invented dV/dt, and I know that dV/dt is 4.5, and I'm told cubic feet per minute. Feet per minute. And my grid is really small. Take your time in writing the grid. I just recognized I forgot to fill in this value. All I need to do to fill that in is put R in there. I'm just going to pause the video real quick, and I'm going to do it, and then I'll be right back. So I just did a quick problem, and I found that the volume when the radius is 2 is 32 pi over 3 cubic feet of air that is currently in the ball. So the last thing that I need to really consider is find the rate of change of the radius. Find the rate of change of the radius when the radius is 2 feet. So the rate of change, so the change in the radius over time. And that's the last thing that I'm looking for. And it's actually my unknown. So it's the change in the radius over time. And again, my time is in minutes. And the change in the radius over time. Okay. So I'm going to scoot this up just a little bit because I have all of the information that I need to know, and I'm looking for this dr/dt. The radius is going to be feet per minute. Because radius is a linear measurement. It's a flat measurement. It's not a volume or area or anything like that. Boy, I'm stuck. I know that I have dV/dt, I have R and V, and the only thing that links them together is, you guessed it, this formula right here. And V, the subsphere, the word sphere, is just an indicator for me to know that this is the volume of a sphere versus a circle or something else. So if I'm going to take the derivative, so if V equals 4/3 pi r cubed, my step is take the derivative with respect to time. So dV/dt is the derivative of V with respect to time. 4/3 pi are just constants. Those are just numbers. And then the derivative of r cubed with respect to time is 3r squared times dr/dt. And I hope you can see that the 3 and the 3 can cancel out, and I can rewrite this as 4 pi, because that's what's left over, r squared dr/dt. And so I now have dV/dt. I can see it in the values up here, and I have the r, I have r, and I'm looking for this. So all it is at this point is a plug and play. It's all about plugging and making the values that I have work into the equation that I have. So I know that dv dt is 4.5. I know that equals 4 pi times the radius, or 2 squared, times, my thing of interest is the rate at which the radius is changing over time, dr dt, and I have numbers, and I have a dr dt, and from here, it's just a bunch of number crunching. So I have 4.5 equals 16 pi. 4.5 equals 16 pi times dr dt. I'm going to divide both sides by 16 pi, divide both sides by 16 pi. I have dr dt is equal to 4.5 divided by 16 pi. And if you wanted to get really specific, I'm going to toss this into a calculator. You would get 4.5 divided by 16 and pi. You'd get 0.0895, and that would be feet per minute. 0.0895 feet per minute. So, to summarize, when the radius is 2 feet, if I'm pumping air in at a constant rate of 4.5, when the radius is 2 feet, my balloon expands at a speed of 0.859 feet per minute. That's probably less than an inch of per minute. Big problem. All I had to do, it takes a long time to do, but I had to just stay super organized, and then it's a plug and go. All right, one more problem, and hopefully you'll have a few examples to look back on. This is another classic problem. We're going to read through it and add our table. I'm just going to add the table right away. An airplane is flying on a path that will take it directly over a radar tracking station. And it looks like in our picture here, this is our radar tracking station. The airplane's flying this way. And so there's one of these tracking stations in Auburn, if you didn't know that. If S is decreasing at a rate of 400 miles per hour, when S is 10 miles an hour, what is the speed of the plane? And in this picture, they're very good about telling you how high off the ground the airplane is. It's 6 miles, and that's going to be pretty important. And X is how far it is on the ground. So we've got a lot of things happening here. I'm going to just pay special attention that we have a variable S, we have a rate, and we know a value for S. So I'm going to first decide that this is something that is important and known. And we want to know the speed of the plane. I wonder where that shows up in this picture, and I suppose we'll get back to it in just a moment. S is decreasing at a rate of 400 miles per hour. So what is S? S appears to be the distance to the station, distance to station. And that is represented by S, and the value that we know about S is 10, and S appears to be in miles, because the units that are predominant are in miles. We also know, we know a rate, 400 miles per hour. S is decreasing at a rate, so we know ds dt, the change in the S over time. So the change in S, or distance over time, S distance over some period of time. We know that for sure. We know ds dt is decreasing. So decreasing, this is tricky, but it's decreasing at a rate of 400, and then the units are miles per hour. Now, I did negative because it's decreasing, and I want to somehow, the way that I notate decreasing in math is with a negative symbol. All right, so I have other things that I need to know. I have x here, and I'm sure that's going to be important. What is x? X appears to be the distance of the ground distance of the plane to the station. So ground distance from the station to the airplane if it goes straight down, and I don't know what that is quite yet, but this seems to be a right triangle, so I suppose I could figure it out using the Pythagorean theorem. The units of this are probably going to be miles. And what is it exactly that I'm looking for? The speed of the plane. That's really important because the speed is ground distance, yeah? So the change in the ground distance over time. So change in ground distance over time, we know that is speed, and we're going to call that dx dt. It's the change in the ground distance over time. This is the thing that we don't know that we're looking for, and the rate is going to be miles per hour, because that kind of makes sense within the context of this problem. So we've got an unknown that I need to know, probably the ground distance or some information. So we know how to find distance. We know that x squared plus s squared, x squared plus 6 squared is going to be s squared. That's the Pythagorean theorem in action. And we know that s is 10. So I'm going to go erase that and say, I know that s is 10 based on this. So 10 squared, because I'm told up above. And so x squared is going to be 10 squared minus 6 squared, so that's 100, minus 36 is, minus 36 is 64. 64, and then the square root of 64, because then I get x is going to be 8, which is nice for us. So the square root of x squared is equal to the square root of 64, and x is going to be 8. So that's really handy. I now know that x is 8, which I didn't know before. All right, so how do I relate ds dt to dx dt and all of these other things? I'm looking for an equation. Oh, wait. We literally just used something that could help us with the information that we want to know. And it gets a little tricky at this point because I know that the distance to the station, the s value, is changing all the time, and the speed of that is changing all the time. So I have to be really careful here, is that I know that my x squared plus 6 squared equals s squared is going to be something that is going to be valuable for us, because when I take the derivative of this over a period of time, I'm going to get the derivative of x squared is going to be 2x dx dt, and the derivative of this is going to be 2s ds dt. We'll actually take that derivative right now. 2x dx dt plus the derivative of 6 squared is just a constant plus 0 equals 2s ds dt. And it appears that I don't need any more information because I know x. We just figured that out. I know I'm looking for dx dt. I know s is 10. And I know ds dt is 400. So I'm using all of the information that I have to simplify this problem with information that I know. So 2 times my x value is 8. Dx dt is the thing that I'm looking for, and it's what I'm going to solve for, is equal to 2. I know my s value. My s value is 10. And I actually know ds dt is negative 400. And now it's just a matter of solving for dx dt. So I'm just gonna divide both sides by 2 times 8. That's just 16 divided by 2 times 8. And dx dt, the interest point, the ground speed over time, is changing at 2 times 10 times 400, so that's 20 times 400, which is negative 8,000 over 8 times 2 is 16, and I'm going to put this into a calculator just to be extra sure that I get it right, but negative 8,000 divided by 16 is going to be negative 500. And what are the units on this? It's negative 500 miles per hour. So my answer to this problem: how much is the ground? What is the speed of the plane at that point in time? It's getting closer. That's the negative part. It's getting closer to the station at a rate of 500 miles per hour. This was a pretty typical related rates problem. I know that they take a very long time to solve. Thank you for sticking with it. Find several, practice them, implement them, be highly organized, read the problems incredibly carefully, just to ensure that you understand where these numbers are coming from. Practice makes perfect. Actually, perfect practice makes perfect. So check in every time you need support. Feel free to send me an email, rgermani@fwps.org, and I will be happy to check through some of your solutions. Good luck, and I will see you next time.